Okay, Ivan, start our seminar. Okay, let us start our seminar, and our speaker, Professor Youjin Zhang from Tsinghua University. You can start.
Thank you, Andre. So the title of my talk is Linear Reciprocal Transformations of Bihamiltonian interval hierarchies. So I will base my talk. Let me see why I cannot go down.
Probably you should just click.
Yes, let me see. I'll go down. Okay, now it's okay. So this talk is based on joint work with Xi Liu and our student, Zhou Wang. So based on the main papers are these three papers. So one is on the variational bihamiltonian cohomologies and integral hierarchies. The first one, foundations. And the second one is also the same title, but we consider variational symmetries using this so-called variational bihamiltonian cohomologies. And the main content of my talk, today's talk, is based on this third one, which will appear soon, I think, on reciprocal transformations of bihamiltonian interval hierarchies. So let me record what we mean by this name reciprocal transformation for PDEs, actually. So we are considering certain evolutionary PDEs of this form. So we have for n unknown functions, u1 to un, and we have a special variable x and time variable t. So if this evolutionary PDE possess two conservation laws, A and P, so then we can change the independent variables, x, the special variables, and also maybe t, the t variables. So we perform this kind of transformation from xt to some new independent variables, y and s, which depending on xt and u, the unknown function. So by this formula, so the differential y is given by this different form of formed by the conservation laws A and P. So such kind of transformation, the change the spatial and time variables of PDE is usually called reciprocal transformations, and it is used widely in gas dynamics and other fields of physics. So in some special cases, we obtain the so-called holograph transformations, which also well known. Maybe well known now, more people know this name holograph transformation than reciprocal transformation for PDEs. So let me explain this special case. So when we have only one unknown function u, then we can take actually u as a special variable, and then the time variable is fixed, still t, and we can use x, the original special variable x, as a dependent variable. So for example, if we consider this quadrilinear PDE, okay, and then we can perform this exchange of this special variable and the independent variable x and u. Then we can, because this transform, we can obtain this Jacobian, the inverse of Jacobian, and we obtain this dependence of this x, the original special variable, on the new special variable y, and its dependence on the new time variable s. And from this equation, we can solve actually because y do not depend, and this is the right hand side don't depend on time variable s, so we can solve it by integrating simply to get this solution of this equation. So this means we can represent this special variable, original special variable x, in terms of the unknown function u, and add an arbitrary function of y, the new time variable. So in this new original notation of t and U, we obtain this relation. So this is again actually given well known given by the method of characteristic, and this f, the function f, is the inverse of the initial function of this U. Okay, when t equals to 0. So this is the most special case of a Hodel transformation. And then we have, if we have two unknown functions, U1 and U2, then we can take U1 and U2 as an independent variable, the spatial variable and the time variable. And we take the original spatial and time variable as a dependent unknown functions of the PDE. So we can perform this reciprocal transformation or Hodel transformation. And for example, we have this quadrilinear PDE. And after this change of the independent variables, and we can linearize this nonlinear quadrilinear PDE to obtain this linear one. So this is also quite often used method to linearize the nonlinear PDEs in gas dynamics. Okay. So the reciprocal transformation that we are interested in is that appear in the study of nonlinear integral hierarchies. So this kind of reciprocal transformation usually help us to establish relations between different integral hierarchies, and also they sometimes they can reveal some geometric structure for integrals behind a certain kind of integral hierarchies. So, for example, the well-known relation, such kind of relation is given by the Kamas-Helm equation. So this is the well-known Shear-Water wave equation in solid theory. And if we perform, so this equation have a conservation law given by transformation, we can introduce a new spatial variable y in terms of this relation and keep the time variable fixed. Then we can transform this Kamas-Helm equation to the negative floor of the KdV hierarchy. Okay, so this gives us important relation of these two solid equations, and also we have other kind of similar reciprocal relation between integral hierarchies. For example, we have two Kamas-Helm hierarchy and the relation with AKNS hierarchy. And we also have well-known relation with the Toda lattice hierarchy with the nonlinear shading hierarchy, and also with the Abramovich lattice hierarchy with these discrete integral hierarchies. So the main interest that we consider such kind of reciprocal transformation is to study certain kind of classification problem that classifies the so-called bihamiltonian integral hierarchies. Okay, so we assume that the integral hierarchy possesses bihamiltonian structure, which possess a hydrodynamic limit. That means they have a leading term given by hydrodynamical type bihamiltonian systems, and the bihamiltonian structure we require them to be semisimple. So such kind of classification problem is solved, and the action of the usual Mueller type transformations, which I will later explain what kind of transformations, and the Mueller type transformations. The obvious of this bihamiltonian integral hierarchies can be described by their leading terms. That means a hierarchy of bihamiltonian hierarchy of hydrodynamic type, together with certain invariants and the Mueller type transformation we call the central invariance of the deformations. So these results are obtained by Dubrovin, Liu, and together with Dubrovin 46, and also we use some. We actually in 2006 we classify this. So this classification problem can be described as we fix a certain leading term, a bihamiltonian hierarchy of hydrodynamic type with semisimple condition, and we consider their deformations. So this means we need to classify the class of deformations of all these bihamiltonian hierarchy hydrodynamic type. So Dubrovin, Liu, and I in 2006 we classified the infinitesimal deformations, and in 2013 we classify this problem for the special bihamiltonian interhierarchy. So that means that this the so-called dispersionist KdV hierarchy, which has a bihamiltonian structure of hydrodynamic type. And then Khalid, Postuma, and Shardling, they solved the general case for a general semisimple bihamiltonian hierarchy of hydrodynamic type. They classified using certain tools by so-called to calculate the bihamiltonian cohomology groups to finish this classification problem. So now we can add this action apart from Muller type transformations. We can also add the reciprocal transformations to consider again this classification problem. So the reciprocal transformation that I mentioned in the previous slides, we can decompose them to two types. One type is we call the nonlinear reciprocal transformations. That if we have one conservation loss of the PDE, of the system PDE, we can do such kind of change of the independent variables. Only change the special variable from x to y and keep the t, time variable t fixed. And then we can compose this kind of reciprocal transform by linear reciprocal transformation, which we can introduce a new time variable y, a special variable y, as the linear combinations of the special and time variable, and also the new time variable as a linear combination of the original special and the original time variables. So this kind of reciprocal transformation we call the linear reciprocal transformations. Okay. So we first consider these nonlinear reciprocal transformations. So for simplicity, let's consider a special linear reciprocal transformation acting on high Hamiltonian system hydrodynamic type. So we quasi-linear PDE can be represented as the action of a Hamiltonian operator on the derivatives of a function h. So this Hamiltonian operator P is this kind. We call it the Hamiltonian structure of hydrodynamic type. So this kind of Hamiltonian structure, infinite dimension Hamiltonian structure, was studied by Dubrovin Novik in the 80s of last century. So they are given by non-degenerate symmetric matrix G, Gi, which the inverse of which gives a pseudo-Riemannian flat metric. And gamma ijk is given by the Levi-Civita connection, the Kirchhoff symbol of the Levi-Civita connection with this metric. So we assume that we have this kind of Hamiltonian system. Okay. Then we can perform a reciprocal transformation, linear reciprocal transformation given by a conservation law rule. Okay. Then a result of Ferapontov and Pavlov say that after this reciprocal transformation, we obtain still obtain the quasi-linear PDE, a system quasi-linear PDE. But again, we have a Hamiltonian structure, but the Hamiltonian operator is no longer local, means that the local mean what we means a local Hamiltonian structure means that the Hamiltonian operator is given by an operator, a differential operator of the special variable x dx. And in the Hamiltonian operator given by Fierpontov to Pavlov, there appear these integral operators of the special variable. So this kind of generalized Hamiltonian structure we call non-local. So, and again, the density is given by original density divided by the conservation rule. So this is the result we know for the action non-linear reciprocal transformation on a Hamiltonian system hydrodynamic type. Okay. And in general, we can consider a nonlinear reciprocal transformation on a Hamiltonian system with the quotient term, and the leading term is a system hydrodynamic type. And we already know that after this such kind of reciprocal transformation, this kind of bihamiltonian system can also be transformed to a Hamiltonian system, but with non-local Hamiltonian structures. And we call such kind of, this is a very special non-local Hamiltonian structure. We call them Jacobi structure. And also we can consider bihamiltonian interval hierarchies. After such kind of reciprocal transformation, they become non-local bihamiltonian. They become a Hamiltonian system, but with non-local bihamiltonian structures again. So to explain this transformation law, let me introduce some notations. So we denote by A the space of differential polynomials on the J space. So we have a finite dimensional manifold M, and then we consider the infinite J space of this. And then if we define this, we define local functionals on this J space. This means this is the quotient of the differential polynomials, the spatial space of differential polynomials by this x derivative with this differential polynomials. And usually we can denote it by this form, the integral of this function, this differential polynomial. And then the local coordinates on this infinite J space, we can use this local coordinates u1 to un is the local coordinates of the base manifold M, and we have just jet coordinates. So you can view this u1 to un as a map from the unit cycle to M, and we have this x derivative of this u1 to un. They're called jet coordinates. And then on this jet space, on this space of local functionals, we can define the multilinear maps, and we denote this space by VP. And on this space of multivector fields, we can define a shortened Nyhaus bracket. Then use this notation, we can define the Hamiltonian structure. A Hamiltonian structure of this on this jet space is given by a Poisson bivector, just as in the finite dimensional case. Okay. Then a reciprocal transformation, we can perform a reciprocal transformation on the space of multivectors, on the space lambda V. So if we have an invertible element of this space of differential polynomial, we can perform a change of coordinates, the spatial coordinates, by this formula dy equals rho inverse of dx, and we can define this new space local functionals lambda y, and then the original space local functionals, we have a natural map from this space to the new space of local functionals by using this map. And this map actually establishes a relation between the Hamiltonian structures to Hamiltonian structures. We can use this map, and this gives a very natural relation transformation law of Hamiltonian structures and the action of nonlinear reciprocal transformations. So a result of Liu and I in 2011 says that if we restrict to a subspace of this Vx is a space of multi-vector fields. So then in this space, this two vectors corresponding to a special kind of Hamiltonian structures we call the Jacobi structures, certain kind of non-log Hamiltonian structures. So our theorem says that this space, this subspace closed and the operation Nyhaus-Richardson bracket or Nyhaus bracket, and the restriction of the reciprocal transformation yields an isomorphism of these two subspaces. So this gives us a natural transformation law of non-local Hamiltonian structures and nonlinear reciprocal transformations. So this means that the result of Pavlov and Verabondov can be given a natural explanation, and their result can be generalized to Hamiltonian systems with dispersion terms, not only a Hamiltonian system of hydrodynamic type. Okay, so this is the case. So this things for our purpose, this result is not so nice because a bihamiltonian structure we consider is always local. We require their local bihamiltonian structures. And but after such kind of nonlinear reciprocal transformation, they usually become non-local. They become a bi-Jacobi structures. Requirement that we hope that our transformation, like the Mueller type of transformation, always change. Bihamiltonian destroys the locality. So, for example, if we consider the KdV hierarchy, the KdV hierarchy, we said that the negative floors of this KdV hierarchy is related to the cohomology hierarchy by a nonlinear reciprocal transformation. That then the reciprocal transformation, the bihamiltonian structure of the KdV hierarchy is transformed to a non-local bihamiltonian structure for the cohomology hierarchy. But actually, both of these interval hierarchies have local bihamiltonian structures. But these local bihamiltonian structures are not related by these nonlinear reciprocal transformations. And up to now, actually, we do not understand very clearly such kind of relation, how to relate these non-local bihamiltonian structures. But these bihamiltonian hierarchies are related by non-linear reciprocal transformations. And but the relation of these local bihamiltonian structures are not clear for us. Okay. So however, if a bihamiltonian structure with hydrodynamic type is transformed to a bihamiltonian structure under nonlinear reciprocal transformation, that means that they are not. If this nonlinear reciprocal transformation do not destroy this non-locality, do not destroy the locality, and then this kind of reciprocal transformation preserves the so-called central invariance of this bihamiltonian structure. Okay. So this is the nonlinear ones. And now let's turn to the consideration of so-called linear reciprocal transformation. So for linear reciprocal transformation, we can consider this the simplest one, that exchange the spatial and time variable for a system of Hamiltonian system. So if we're given a Hamiltonian system of hydrodynamic type, then let's exchange this. We can take a t, the time variable, as spatial variable, and x as a time variable. So we can solve this system by write this we can invert this matrix to write this, to represent this ux in terms of ut. So this means that if we take this x, I use x as s, right? This s, then we can write this equation, inverted system, as in this form. So this form quite simple. Yeah, we can obtain this transformed quasi-linear PDE. Then we can ask whether this system still possesses a Hamiltonian structure. Okay. So as a result of Pavlov in 1995 says that if we introduce a new independent variable wi in terms of the original Hamiltonian density of Hamiltonians of the system, so this H is density of Hamiltonian. And then we perform a Legendre transformation to introduce the new density of Hamiltonian. Then this transformed system, I mean that this system can be represented as a Hamiltonian system, okay, with a Euler canonical Hamiltonian operator. Okay. So this means that a Hamiltonian system hydrodynamic type preserves the Hamiltonian property after linear reciprocal transformation. Okay. And then if we have a bihamiltonian structure, so if we are given a system hydrodynamic type which possesses a bihamiltonian structure given by two hydrodynamic Hamiltonian operators, P1 and P2. Then we have two density of Hamiltonians. Then now we perform linear reciprocal transformation, which transform this special variable x as the time variable and the original time variable as the special variable. Then this system again, of course, can be written as after this linear reciprocal transformation, we need to know whether this transformed system still possesses a Hamiltonian structure, bihamiltonian structure. And this is again true that if again we introduce the new dependent variables wi, and we can introduce two flat matrices eta tilde and g tilde in terms of the original one, eta ij and gij. So this original flat matrix gij is represented in terms of unknown function u, and we define this new flat matrix g tilde ij in terms of the new variable w. So we introduce two matrix A and G. Then we, as a result of Ting Xue and I, say that these two matrices again are flat and they are compatible. They use two Hamiltonian operators P1 and P2 of hydrodynamic type, and they're compatible. So, and the original, the transformed integral hierarchy, the Hamiltonian system can be represented as Hamiltonian bihamiltonian systems by using these two Hamiltonian structures. Okay. So this means for a bihamiltonian structure of hydrodynamic type, after reciprocal transformation, the Hamiltonian bihamiltonian property is still preserved. Okay. So, but however, we want to generalize this kind of result to bihamiltonian systems with dispersion terms, not only bihamiltonian system hydrodynamic type. And when we want to try to generalize such kind of transformation law, but we are failed to give a generalization. This seems to be not simple because in this dispersionist case, in this case of hydrodynamic bihamiltonian systems, we construct explicitly the bihamiltonian structure for the transformed system. But for general systems, bihamiltonian systems with dispersion terms, we actually no longer able to construct such kind of explicit formula for the bihamiltonian structures. And we even don't know whether it's true, whether these transformed systems possess bihamiltonian structures. So this is what the question that I answer in this in what follows. So more precisely, the integral hierarchies that we are considering have this form. So it has a leading term. The leading term is given by a system hydrodynamic type, and with dispersion terms with high order x derivatives of this of the unknown functions, and we can perform this linear reciprocal transformation if the leading term, the matrix, is non-degenerate, and we can represent ux in terms of ut to obtain such kind of system. So this system we can consider. We can, because we are in the integral hierarchy, we have different floors. So other floors can also be written in this form. We rewrite the x to ux in terms of ut. Okay, so the integral hierarchy is now transformed to this form, and we are to study whether this if the original system hierarchy of floors possess a bihamiltonian structure. So we then want to know whether the transformed one also possess a bihamiltonian structure. Okay, so this kind of problem, if we consider even in the simplest case, that means that we have only one unknown function, so n equals to 1, then it's still also is not non-trivial, because we don't have a natural way or canonical way to construct the bihamiltonian structure of the transformed system. So, and it's not like in the nonlinear case. The nonlinear reciprocal transformation, we have a canonical way to study, to give the Hamiltonian structure or bihamiltonian structure or the non-local for the transformed system. But for this linear reciprocal transformations, because it also changed this special variable and also the time variable. So this system, the original setting that we use this the space of local function on the infinite J space, we can no longer able to use this setting to study this Hamiltonian structure. So for this case, now we realize that we can study this proper Hamiltonian structure for this transformed system by using certain super extension of the integral hierarchy. Then we can find some quite a natural law that after this linear reciprocal transformation, this kind of linear reciprocal transformation can act in a quite a natural way to the kind of super extension of the integral hierarchy. So what I want to say is to explain this: what is a super extension of an integral hierarchy? So to do this, I need to introduce these certain notations. Again, we're starting from base manifold of dimension m, of smooth manifold m, and we consider its super the associated super manifold by reversing the parity of the fibers of its cotangent bundle T star m. So we have this super manifold, and we consider its case J manifold, J bundle, and then we take a projective limit to obtain the we call the infinite J space. Okay, so on this infinite J space, we have natural local coordinates. We take first take a chart on the base manifold M, and we have this local coordinates U1 to UN on this super manifold, and on this we of this even, this U alpha is even, we call even coordinates. We also have this odd coordinates, theta alpha, on the Cartesian space. So we have this log coordinate for supermanifold. And on the infinite jet space, we have log coordinates or jet coordinates of U alpha, theta alpha, and their jet coordinates. And then we have the linear differential polynomials, okay, with coefficients depends mostly on the coordinates u1 to un, and we have this jet coordinates which can be represented as a completion of differential polynomials, a space of differential polynomials. And on this space, jet space, we have a global vector field dx, so we take a total x derivative. Okay, then we can form the quotient of the space of differential polynomial a hat. Take the quotient space, we obtain the local functionals on the supermanifold. Okay, and on this space of local functionals, we have two natural gradation. One is given by the super variables. The number of depends on the number of super variables given by super gradation. And we also have a natural gradation given by the x derivative, the differential degree d. So we can decompose this space of local functionals according to these two degrees. We call super degrees gradation and the differential gradation, P and D. So this gradation is important actually. Then on the local space local functional, we can define natural shortened Nyquist bracket. So using this variational derivatives of this super variable and the order variables and the even variables. And such kind of shortened Nyquist bracket is preserved and the so-called Mueller type transformation. So a Mueller type transform means that we transform this UI, the coordinate UI to WI by this kind of way. So if we restrict this transformation to the base manifold, this way requires that this is just simply a change of coordinates, okay, on M. Okay. So this change of coordinates on the infinite jet space is also reduced by is given by actually from the change of coordinates on the infinite jet space of M. Not okay. So this kind of transformation you will call the Mueller type transformations. And for the Hamiltonian system evolutionary PDE, we usually write in this form. So it's given by the action of certain Hamiltonian operators on the variational derivative of the Hamiltonian. Then in the language of these log functionals, we can represent it by a certain log functional of super degree 1. That means a vector field x, okay, can be represented in this form. And also this is the flaws of the system, and also the Hamiltonian structure can be represented by a bivector. In this case, it's given by degree 2, super degree 2 local functional. Okay, this means that it's represent in this representative we have two super variables, or the theta 1, theta I, theta j. So. And this P, the bivector is given the Poisson bivector, means that the shortened bracket of itself is equal to 0. And this Hamiltonian vector field is given by shortened bracket of this P, Poisson bivector, and the Hamiltonian H. So the Hamiltonian H is super degree 0 local function. Okay. So this is our representation of Hamiltonian evolutionary PDE in terms of local functionals. And then we call a Hamiltonian structure P is of hydrodynamic type if this Hamiltonian operator have this form. And if we have we say we have a bihamiltonian structural hydrodynamic type, and we say this bihamiltonian structural hydrodynamic type is semi-simple, then we mean that the corresponding metric, the corresponding for these two metrics, the associated the root of the characteristic equation is distinct and non-constant. And then by using a result of Ferpontov, say that we can take lambda 1 to lambda n, these distinct roots of this characteristic equation as log coordinates of the base manifold M. So in the canonical coordinates, these metric G0, G1, these two metric are diagonal. So they can be represented by n functions Fn, F1 to Fn. Okay, and then we can consider so-called deformations of the Hamiltonian structural hydrodynamic type. So if we're given say kind of Poisson bivector of hydrodynamic type, we can consider its deformation. We add some high order super degree, a high order differential degree terms Q. Then we require that this deformed one is still a Hamiltonian structure. Okay, and we regard two deformations to be equivalent if they are related by mirror type transformation, related by simply a change of coordinates. Okay. Then we can also consider deformations of bihamiltonian structure. Okay, and then the result that I already mentioned on deformations of bihamiltonian structural hydrodynamic type of semi-simple one, we have these results of this. I put it in the theorem. That says let P be a Hamiltonian structural hydrodynamic type, and P0, P1 is a semi-simple bihamiltonian structural hydrodynamic type. Then any deformation of this Hamiltonian structure is always trivial. So that means we can any deformation can be reduced by a mirror type transformation. Okay, and also we can consider deformations of semi-simple bihamiltonian structural hydrodynamic type, and it says that the equivalent classes are parameterized by n functions of a single variable, and we call these functions the central invariants of the deformation. This means that these deformations are characterized by these n functions. Okay. They are called invariant because they are invariant and mirror type transformations. Okay. So this is a result we already done on the deformation by Hamiltonian structure hydrodynamic type, and this theorem is actually can be proved by computing some Hamiltonian cohomology or bihamiltonian cohomologies, so similar as in the finite dimensional case. Okay. And also we have classification of bihamiltonian structures, and then this theorem tells us what about the deformations of bihamiltonian integral hierarchies, or about flaws of this hierarchy. So if we have a bihamiltonian structure, and we have a semi-simple bihamiltonian structure, and then if we have a deformation of this bihamiltonian structure, and then if we have also a bihamiltonian vector field X, bihamiltonian flaw, which means that this X is the shortened bracket of this X with P. These two Hamiltonian, these two Poisson bivectors is equal to 0. Then we can consider the deformation of this bihamiltonian vector field. And this theorem says that we have a unique deformation of this bihamiltonian vector field, such that this vector field commute with these deformed bihamiltonian structures. Okay, so this theorem tells us that these deformations of the bihamiltonian integral hierarchies is clear. We only need to know the deformations of the associated bihamiltonian structures. Okay. Now, to study the transformation law of Hamiltonian structures and the interaction of linear reciprocal transformations, we need to consider a more big space. Originally, we consider the space of local functionals. And also we study the space of local functionals. And we can define the bihamiltonian structures. And we can consider the deformations of bihamiltonian structure by using certain so-called bihamiltonian cohomology groups, which is defined also on the space of local functionals. But this setting is not enough for us to consider transformation law of Hamiltonian structure or bihamiltonian structures and the reciprocal transformations. So we need to extend this space of local functionals. Now we have to consider the space of evolutionary vector fields on the infinite jet space, actually. So it means that we consider derivations. We did not by this symbol. And an element of derivation means that there are linear maps on the space of local functionals ahead, not local on the space of differential polynomials of the supermanifold. Okay? And its action of it's act on some degree. So if X it belongs to the super degree P, it acts on this degree super degree Q differential polynomial to P plus Q. So, and this we call it evolutionary vector field. It means that this vector field commutes with dx, so total x derivatives. Okay. So, and also it satisfies the super Leibniz rule. If we have two differential polynomials f and g, and then x act on this product of g and f have this formula. And this space, on this space, we already define this super degree, and also we have a differential degree. Okay. Then we have actually a canonical map from the space of local functional to this space of derivations of the space of evolutionary vector fields. Because on the supermanifold, we have a canonical symplectic structure, omega. And using this canonical symplectic structure, we can define this map D. We can map this any log functional x to a derivation of the acting on the spatial differential polynomials. And this the image of this map gives a subspace, and in this element of this space we call the derivations of D type. Okay. And this kind of derivations corresponding to actually in the finite Poisson manifold corresponding to Hamiltonian vector fields. Okay. So the general derivation corresponding to evolutionary vector field. Okay. Then using this setting, we let's consider the so-called super extension of a Hamiltonian system. So if we are given an evolutionary Hamiltonian PDE, so such kind of PDE can be given by a super degree 1 local function x, and also super degree 0 element h so as Hamiltonian, 2 a log function p as given by a Hamiltonian structure. And the relation this vector field x and ph is given by. We can because we have these log functionals x and p, then these two log functionals gives us two derivations dx and dp. So this derivation given by this map. Okay, so we have these two derivations, and then we can define the original evolution flows can be represented as a derivation dx acting on ui, and we can act this derivation on theta I, the order variables, and we obtain the flaws of theta I along this time variable t. And we also introduce, by using these derivations given by the Poisson bivector p, and we can define an evolutionary flaw of the ui along a new time variable tau, we denote by tau. So this is a super time variable. And we obtain this evolutionary vector field, dpui and dpci. So in this way, we obtain a so-called super extension. So this is the original evolutionary PDE, and we add on this to this evolutionary PDE some original flaws, so original time flaws, which we can see this evolution of the order variable theta I along this original time variable t. Then we also introduce another order flaw, tau, d tau. We have this evolution of the original unknown function ui and the order variable theta I by using this derivation dp. So this we have this super extension of the evolutionary PDE. And these flaws are commutative because we have this commutativity of this x and p. Okay. Then we can also define certain cohomology because we have this differential dp. Okay, by using this adjoint action of this derivation dp. Okay, because dp and dp, these two, this derivation, this order derivation is commutative with respect to the shortened line bracket. We have this dp as a differential, and we have a complex formed by on the space of evolutionary vector fields or the space of derivation. Okay. Using, and this is that means given a Hamiltonian structure hydrodynamic type, we have this complex, and also if we have a bihamiltonian structure given by p0 p2, and then we have a bicomplex formed by this differential dp0 and dp1, and these complex, for this complex we have these cohomology groups. We call these cohomology groups the variational Hamiltonian cohomology group, and also the variational bihamiltonian cohomology group. Okay, so these variational bihamiltonian cohomology group and also this variational Hamiltonian cohomology groups will be used to for a study of transformation rule for Hamiltonian or bihamiltonian structures and linear reciprocal transformations. Okay. Then the first thing that we need to know is we need to compute this variation of bihamiltonian cohomologies. And this computation is not trivial, actually it's quite tricky. Anyway, we can compute it by using the follow the method of computing bihamiltonian cohomologies. Okay. So theorem of Siqi Liu, Zhou Wang, I say that for this Hamiltonian variation Hamiltonian cohomologies, they are trivial. Okay, and for the variation of bihamiltonian cohomologies, we have some non-trivial cohomology groups. Okay, and other cohomology groups are trivial. So these cohomology groups is that we need. Of course, we have not computed not all variational bihamiltonian cohomology groups. We only computed this degree 1 and 0, and also the high degree ones we have not yet computed. But the computation can be done by in a similar way as we compute the bihamiltonian cohomologies. Okay. Then let me explain this our consideration of transformation law of Hamiltonian structure and linear reciprocal transformations. we are already prepared. Then let me use a simple example of KdV equation to explain our way how to study this transformation laws of Hamiltonian structures. So let me consider the Hamiltonian the KdV equation. So this equation is we have a unknown function u and time variable t, and it has a bihamiltonian structure given by these two Hamiltonian operators P0 and P2. Okay, and then in our setting of local functionals, this KdV equation, this flow can be represented by this vector field x, super degree 1 local functional, and also a super degree 2 log function of P0 and the super degree 2 log function of P1. So the P0, P1 are Poisson bivectors. And then we can extend this KdV equation, the original KdV equation, to a super extension. So we have this KdV equation, and the other variable, a super variable, have this evolution around this original t. And also we introduce two additional super time variable t, tau 0 and tau 1, given by this the derivations given by these two Hamiltonian operator P0, P1. So this evolution of u along this tau 0 given by theta 1, and the evolution of theta along this tau 0 is 0. It's trivial. And we have also this order flow given by the tau 1. I have a mistake. This should be tau 1, induced by this Hamiltonian operator P1. So we have evolution of u along this tau 1 given by this expression, and this so this is called super extension. Then we make a change of the spatial and time variables. We now view this x as a evolution as t, and t as a spatial variable. Then we can rewrite this system. We can represent this ux in terms of ut, and theta x also in terms of theta t. Okay. Then we can represent this original super extension of the KdV equation in terms of given we have obtained this new transformed super extension. Okay, so this original x we rewrite this original we write back this t as x, and this x as a new time variable t tilde. So we obtain this certain super extension of the KdV equation after this reciprocal transformation. And then if we already know that these flows are of D type, so this means this right-hand side are given by certain derivations of the infinite jet space, certain evolutionary vector fields. Okay, and then if these vector fields are of D type, means that they are obtained from the map D from a log functional to this vector field. Or in other words, if we have log functional like tilde, P0 tilde and P1 tilde, so that these flows can be represented as the derivations of dx tilde and dp tilde 0 and dp tilde 1, acting on u and the theta. Then we obtain the bihamiltonian structure for the transformed KdV equation. So this is the way we consider this transformation law. This is actually quite natural, but actually this transformed system in the coordinates, original coordinates u and u and theta. Theta is the order variable. U is the even one. Is actually not D type. The right-hand side, these vector fields are not D-type vector fields. And to to remedy this problem, we need to introduce a new order variable sigma instead of theta. We define new order variable theta by using this formula. This relates this order variable, original order variable theta with a new order variable. Then after using this new order variable, we can represent this original transformed super extension of the KdV equation. Right, instead of theta, we write the sigma as using this sigma, this order variables to represent it. And then it turns out that the transformed, since this new representation of this vector fields, evolutionary vector fields are non-p-type. That means that we can find certain local functionals x tilde, p0 tilde, and p1 tilde to represent these flows as derivations of this form of d-type. So in this way, we obtain the Hamiltonian bihamiltonian structure of the transformed KdV equation. So we obtained this these p0 and p0 tilde and p1 tilde. It's a bihamiltonian structure. Okay. So this is the basic idea that the way what we are doing, how we do to find the existence of bihamiltonian structures after linear reciprocal transformation. So in general, we can do this. We're starting from bihamiltonian, semi-simple bihamiltonian structure hydrodynamic type, and we represent this bihamiltonian structure in the canonical coordinates. Then the associated metric is then a diagonal. We can represent this diagonal metric by f1 to fn. And this diagonal metric have the rotation coefficients, we denote by gamma j. Then it turns out we can perform for this given this bihamiltonian structure hydrodynamic type of semi-simple one, then we can consider this bihamiltonian vector field. So it turns out if x is a bihamiltonian vector field, then this x must be represented in this form. And the coefficients AI can be represented in terms satisfy this system equation given by the rotation coefficients and the metric. Okay. And then by using this property, then we can consider this the reciprocal transformation acting on this kind of bihamiltonian system hydrodynamic type. And we can consider its super extension, and we can transform, perform this reciprocal transformation on this super extension, and study its this existing bihamiltonian structure. Similarly, we need to introduce a new order variable sigma I, sigma 1 to sigma n in terms of the original order variables. Then by using this method, then we can obtain the original order theorem given by Tingshu and I in 2006. So that means that given semi-simple bihamiltonian structure hydrodynamic type, and with a bihamiltonian vector field, then if we assume that these AI are non-zero, then we can perform a reciprocal transformation to obtain the evolutionary PDE of this form. And this evolutionary PDE admits a bihamiltonian structure. And this bihamiltonian structure is given by the flat pencil. These two metrics are given by f tilde 1 to f tilde n are related to the original f1 to fn by this formula. And also the important property is that this transformed flat metric and the original flat metric has shared the same rotation coefficients. So that means that for bihamiltonian structure hydrodynamic type, after reciprocal transformation, it also again transformed to a bihamiltonian structure hydrodynamic type. and the rotation coefficient is invariant. Okay, so this is we consider the case of hydrodynamic type case, and for general bihamiltonian structure with the dispersion term, we can consider in this way. We are given two vector field, evolution vector field in this spatial derivation. Okay, and then we have obtained the bihamiltonian structure given by this superflows d tau 0, d tau 1, which are represented by two super degree 1 derivations. Okay, and we require that this is this Hamiltonian structure means that these brackets are 0, and this vector field is bihamiltonian vector field. This means that this bracket, shortened bracket, is 0. And we also require that these structures has hydrodynamic limit. That means that they can be decomposed by using the differential degrees. Okay, and then we have a theorem that assumes that we, in terms of the local coordinates of ui and theta I, these derivations can be the leading term of this bihamiltonian vector field, and the bihamiltonian structures are of D type. Means that we have they are corresponding to a hydrodynamic type semisimple bihamiltonian structure and Hamiltonian vector field of hydrodynamic type. Then we can perform a change of the order variables. We can perform always exist a transformation of order variables, so that in the new variable or the new order variables, these flows, the original given flows of this original this time the flows and the Hamiltonian vector fields becomes of D type in this new order variable sigma I, okay, of D type. So this theorem gives us a way to study the deformations. So we already know the leading terms, how the leading terms are changed after a linear reciprocal transformation for the KdV bihamiltonian structures and also for the bihamiltonian flows. Then to study the dispersion terms, the transformation rule of the dispersion term for the bihamiltonian structure and also the bihamiltonian flows, we can use this theorem because we can perform a change of the order variables to always to transform the whole bihamiltonian structure and the bihamiltonian flows to a D type flows. Then using this theorem, we can prove this result, that the main result I am to explain. So assume that we have a bihamiltonian integral hierarchy with hydrodynamic leading terms, and that these leading terms admit the semisimple bihamiltonian structure of hydrodynamic type. Then in these flows, we can pick a non-degenerate flow from this integral hierarchy and perform linear reciprocal transformation with respect to this particular flow. We do this linear reciprocal transformation to the whole hierarchy. Then we obtain another integral hierarchy. These flows still commutative. And then our results say that then this new integral hierarchy is again bihamiltonian. It has a bihamiltonian structure with hydrodynamic limit, and its bihamiltonian structure has semisimple hydrodynamic limit. And moreover, the central invariants of this new bihamiltonian structures are the same as the central invariants of the original bihamiltonian structures. That means that the linear reciprocal transformations preserve the bihamiltonian property and also preserve the bihamiltonian central invariants of the bihamiltonian structure. So this theorem gives us a clear picture on this transformation law for bihamiltonian structures are after linear reciprocal transformations. Okay. So, however, we do not know the explicit formula. This theorem, of course, only gives us the existence theorem, not the constructive. We do not have a constructive results on these transformed bihamiltonian structures, unlike in the leading term. For the leading term, we do have. Okay. Then for this, by using this result, we can consider the classification problem of bihamiltonian hierarchies. So originally, we only use Muller type transformation. We can only consider equivalent class and the Muller type transformations. And now we can add this linear reciprocal transformations. So then after this transformations, then the equivalent classes by bihamiltonian integral hierarchies are actually characterized by the so-called rotation coefficient gamma ij and the central invariants. Okay, these rotation coefficients are a set of function gamma ij satisfy this system of nonlinear PDEs. Okay, so this gives us this more fine result on this classification of bihamiltonian integral hierarchies. And so because the time I'm already exceed the 10 minutes, then I very briefly explain the example I consider Volterra hierarchy and its relation to the negative flow of the KdV hierarchy. So this can be related by a linear reciprocal transformations. So the Volterra hierarchy have this is the Volterra equation. It has a bihamiltonian structure, and we pick some flaws of this hierarchy or symmetry of this hierarchy, and then after this using this reciprocal transformation, we can transform this Volterra, the original Volterra equation, okay, this Volterra equation to the first negative flow of the KdV hierarchy, which is represented in this form. And also we can show that this negative flow of the KdV hierarchy, we have the bihamiltonian structure. This is transformed from the bihamiltonian structure of the KdV of the Volterra hierarchy. So of course, this bihamiltonian structure of the negative flow of the KdV hierarchy is the same as the bihamiltonian structure of the KdV hierarchy. Okay. And also the last theorem that I want to present is also we consider the problem of bihamiltonian integral hierarchy and what condition we can transform it related with a bihamiltonian integral hierarchy associated with a semisimple Frobenius manifold. So for a semisimple Frobenius manifold, we can construct a bihamiltonian system hydrodynamic type we call principal hierarchy. And this principal hierarchy has many deformations, bihamiltonian deformations. And one particularly important deformation is called the topological deformation. It corresponding to integral hierarchies that control to the topological field theory. So when we ask, given a semi-simple bihamiltonian integral hierarchy, under what condition it is related to the topological deformation of the principal hierarchy of a certain semi-simple Frobenius manifold, and the Muller type transformations and the linear reciprocal transformations. And the answer is that this semi-simple bihamiltonian hierarchy, for this integral hierarchy, the central invariance of this integral hierarchy, the bihamiltonian structure should be 1/24. And also, we have the rotation coefficients of the flat metric of the first Hamiltonian structure, and we need to require that this rotation coefficient should be symmetric. I mean that is given by the Golov metric. Okay, and also these rotation coefficients satisfy the so-called irreducible condition. Okay. Okay. So this is the condition that that we need to relate the bihamiltonian structure to a semi-simple probability manifold. So, for example, the well-known soliton, discrete soliton interval hierarchy, the Abreu-Gileadic hierarchy, can be related to the well-known total lattice hierarchy and the nonlinear Schrödinger hierarchy, which are well known. They are related to semi-simple probability manifold. Okay. Okay. So so this is what I want to talk on this seminar. Okay.
Okay, thank you. Thank you very much. Very interesting talk. Okay.
Yeah.
Youjin, can you send to me the slides of this talk?
Of course, yeah, I can send you.
Okay,
Yeah.
thank you very much. Okay. Any questions? Any comments? Okay, no questions, no comments, because we have not Grigory Sharigan. Who
Yeah. So
yes.
because this time in China, we have students have dinner time. So
Oh, sorry,
students
sorry.
are not coming. Yeah.
Sorry about.
In Europe, is noon. Yeah, it's 12, 1 o'clock.
Okay, okay. Thank you again. Okay, let us finish our seminar. And Youjin, thank you very much.
Yeah, welcome.